Hello all. It's a miserable, windy and wet day here in Armidale, so it's nice to be inside and at home. Um, and welcome to the second lecture of the week. Today we'll talk about regolith processes, official deposits, so this should help with that practical quiz that needs to be completed. So we'll look at a few things. Broadly, laterites, bauxite, so these include nickel. We'll touch on magnesite deposits. We'll also look at supergene and placer or mineral sand deposits. So these can be broadly considered as sort of a secondary process, but they have huge advantages. There's limited overburden, they're quite easy to extract, it's unconsolidated material, and they can, in the case of supergene deposits, actually make porphyry systems profitable, at least initially. Okay, so these official deposits are associated with weathering and different climatic environments will have a big bearing on the styles of mineralization and the nature of the ore body. So some, like bauxite, which is essentially aluminium ore, and nickel laterites, quite common in humid, warm, tropical areas. Magnesite, on the other case, is slightly more arid, and well, I'll get into this in a bit, but those variability in rainfall and dry spells can influence the grade of these deposits. Additionally, we have oxidation, where coming from a system which is fairly reduced and exposed to the atmosphere, so this causes substantial changes in the mineralogy. We get pronounced hydration of minerals. Feldspars might go to clay, kaolinite, and things like this, and we might also oxidize them at the same time. So many of the secondary ore minerals are hydroxides or oxyhydroxides. So they're they've been oxidized and they've also been hydrated. So the broad idea is that, at least initially, if we have rocks that are progressively weathering, we can mobilize certain elements. They're leached from the profile, and the other ones are retained. They're relatively immobile and they concentrate. So we might leach things like potassium, sodium, and calcium, and we might be able to have a residual enrichment in things like titanium, or aluminium, or nickel, or even gold, or PGEs. So it's that residual enrichment that can actually concentrate a fairly standard rock type into a high-grade ore for aluminium. And so it's a bit of a play on this, and that's dependent on the weathering environment. So there's a complicated series of mineralogical changes that goes on. I'll just note that the regolith environment is essentially the overburden in geology. So Australia has very prominent regolith profiles. Many of our rocks are very old, and they might have spent upwards of 100 million years at the surface, progressively being weathered and broken down into soil products. So there's been a big push in Australia over the last sort of 20 or 30 years to have better understanding of regolith processes. One, for looking for deposits in them, and also for us to try and identify rock types beneath the regolith that we in Australia. But like I said, we have this situation where we're potentially hydrating and oxidizing minerals, so we're getting these breakdown products. So we have things like feldspar that probably would go to kaolinite, so clay. We have sulfides and amphiboles and chlorite that are probably releasing iron that can form goethite, so iron-rich clay. We might also get other minerals like smectite, but also we can release aluminium to form gibbsite, which is essentially hydrated aluminium. So we have circumstances in most laterites where we're worried about gibbsite versus goethite, so the proportion of aluminium versus iron that forms. Many of the other minerals, we might get a limited change. They're fairly happy. Ilmenite might go to anatase, but talc, zircon, and chromite and things like that might be stable as we go from a bedrock into higher proportions of the laterite profile. So here is a standard sort of regolith or weathering profile we call a laterite profile. We start at the base, we have a parent rock, and depending on the type of deposit, the parent rock has a big influence. So for things like bauxite, we might want something quite enriched in aluminium, so it could be a basalt, or it could be a granite. For things like nickel, we need an ultramafic source because there's not much nickel in most granites. So we need serpentinite or some sort of ultramafic rock for us to get high nickel content. So that's the first important factor. So at some stage, originally, the parent rock encompassed this whole volume. And progressively, in tropical environments, we have high rainfall, we might have groundwater percolation, and we might get periods interspersed of rainfall and dry periods that can progressively weather this rock profile. So we go into a zone we call a sap rock zone, where we can actually see remnants of the original rock texture, but it's predominantly transformed to secondary minerals, could be kaolinite or a variety of other oxyhydroxides. We then move further into the saprolite zone, so we're getting predominantly breakdown, limited textural variability. We go into a mottled zone, indurated area, and we have the piezolitic crust. So this is iron rich. We go further down, we have concretions and accumulations of material that was probably residual in the mottled zone, and then we have most of into the sap rock and saprolite area. So essentially what's happening is water is percolating through, we're breaking down, by hydrolysis or the primary minerals, we're weathering them, and progressively we actually leach mobile elements like sodium, calcium, potassium, and they're leached out of the profile, and we're left with residual material, which is commonly aluminium and iron. And so if we have high enough aluminium concentrations, we can form a bauxite deposit in these upper areas, and I'll show a picture of that soon, where we can actually form gibbsite, so aluminium, hydrated aluminium, and we potentially also have goethite. This is where the climate becomes very important, that we need high rainfall. If we have very high rainfall, we can actually leach out the iron and be left with residual higher aluminium grades. If the environment is more arid, iron is maintained in the upper bauxite region, and the grades of aluminium are too poor. Other minerals like gold can also be liberated, also platinum group elements, or nickel. They can sort of be concentrated further into the laterite profile, where they are precipitated or reacted out in clays, and they bind in and they are preserved in the saprolite zone. But remember, we need an ultramafic source. So this is the broad considerations of laterite deposits. They're very important. Probably one of the things that is most commonly sought. I discussed in the last lecture about how important nickel price is at the moment, but aluminium is very fundamental. As we can see, many products use aluminium, and so they're very important deposits and very economical ways to mine aluminium. So I won't carry on to this in too much detail, but here gives you an idea of the element mobility in the weather terrains in different positions. So the weathering fronts, we have minerals that will be leached And then we have minerals that are retained and therefore residually enriched. So in the lower saprolite, we might be enriched in aluminium, and in the mottled zone, see up here, we're getting silica and aluminium, so we're in this stable bauxite area. Further down, we get into nickel, cobalt, etc., titanium, vanadium. So they're the regions that you'd be looking for nickel laterite deposit. Here's an example from Weipa, prominent bauxite mine in northern Australia. So here is a photograph of a laterite profile. We have bauxite at the top, so this is high, probably predominantly gibbsite or bormite, as we can see here. High concentrations because we've residually maintained aluminium and we've leached out most of the other elements, including iron. Then we transition into the mottle zone and further down towards where the actual saprolite or saprock is down here. So this is the regolith profile, and here you can see broad mineralogical change. We go from gibbsite, high aluminium grades, we get kaolin, quartz, kaolinite, glauconite, and smectite further down. So we have changing proportions, particularly with the iron oxides, to make this economical for aluminium. For nickel deposits, we need initially this ultramafic source. So one of the most prominent nickel laterite deposits occur in New Caledonia, where we have one of the largest ophiolites or oceanic material abducted onto the continent there, and it is in a tropical environment that enables high rates of weathering, and we can actually mobilize a bit of the nickel and residually enrich it and essentially bind it in a variety of minerals that we call garnerite. These are various hydrated silicates, could be clays, can be serpentinite, can be talc, and it's enriched in this saprolite zone. So that's where it's more important for nickel versus aluminium. Here's just an example showing the variability in the concentrations. So we have our Harzbergite, peridotite down here. We have our upper piezolitic portion of the laterite profile. Here, the nickel concentration is increased right here in the saprolite area, where we get these hydrated nickel-bearing minerals. Cobalt might be a bit further up in the sequence in the laterite zone, and you can see here the iron concentration progressively decreases because iron is being residually enriched further up. Silica is leached, and aluminium, we have a broad peak here, but these rocks are generally poor in aluminium, so they're unlikely to present as a bauxite deposit. Okay, the alternative for many ultramafic systems, particularly here in the New England area, where we don't have as high rainfalls, are what we call magnesite deposits. This is essentially magnesium carbonate, okay? And they're used for a variety of reasons. Soil neutralizer, burning magnesium metal, magnesium bricks. And it is a product of the weathering of ultramafic substances, and it's formed in arid environments, unlike nickel laterite. So we have a drier system, means we probably have lower rates of leaching, and we can derive carbonate, CO3, from organic or atmospheric carbon. And it forms in these sort of nodules and veins, and in most cases it's subeconomic, but it's in the saprolite zone. In the humid environments, the magnesium is soluble and removed, so we can't actually form magnesite. It's lost from the system. And it's worth noting that this is one of the primary, well, this is a method that people perceive can be used as a carbon sequestration method. If we go to these ultramafic complexes and we can actually pump CO2 into them, we can form magnesite and capture carbon. The major pitfall is, to do this, you have to disaggregate large swaths of ultramafic material to get the surface area suitable for the energetics of the reactions to incorporate CO2 into with the magnesium. So it's energetically inhibitive or prohibitive from a start point to break up that rock so much. So you're possibly not actually doing much carbon capture when you really look at the net effect. Here's just an example of magnesite, the white area here. It's fairly fine grained, soft, and it's forming these sort of nodular areas here where we might have a bit of serpentinite preserved. Okay, moving on slightly, but to a similar style process, we're going to look at supergene. Now this is more specifically around an exposed ore body, whereas bauxite, nickel laterites, and things like that are general common rocks going through a weathering. So supergene deposits are very important for things like copper because they can actually make porphyry systems economical. So the supergene effect concentrates ore, particularly copper, maybe also gold, sometimes silver. And they can mine that initially, make money, and then move into the primary ore or the hypogene zone, which is probably copper as chalcopyrite or in the sulfides, where whereas extraction costs are probably higher. So what happens is we have the ore body essentially exposed at the surface. It's being oxidized, and we have a groundwater effect where we can leach copper out of this area, and it will go down to about where the water table is and precipitate out as secondary copper minerals. So the chalcopyrite, the sulfide, it's unstable in the oxidizing conditions. We can release cuprous material, and it reprecipitates as a variety of different secondary minerals. In this area, commonly chalcocite or cavellite, but we can also get things, if there's CO2 around, we can get azurite and malachite. People will be aware of the bright coloured material, and we produce initially a supergene blanket above the hypogene deposit, and we also produce what is called a gossan. So the gossan is the eroded, oxidized, rich material of the ore deposit that people usually use to distinguish that there's a deposit there. So here's just a diagram looking at supergene copper and the stability of copper relative to redox conditions and pH. So down here we have our sort of we can have our standard sort of chalcopyrite we'll take, for example, or bornite. If we increase the oxidation, we progressively find cavellite, chalcocite, and we might just get cuprite as we go towards atmospheric conditions. We can also get malachite and things like that. And depending on the nature of the pH, remember that eroding sulfides can change the acid nature of the fluids because we can cause hydrolysis. We can also change the style of minerals. And then these minerals will further break down to get malachite and things like that. And that's commonly what's seen in supergene blankets for most porphyry deposits. And so here's an example. Here's our leach zone. This is predominantly gorthite, so iron-rich sort of gossan. We go down into the green oxidized zone where we have our copper-rich solutions under oxidizing conditions, and they can then precipitate out as secondary sulfides under reducing conditions as we get further down into the water table zone. So this green area can present as a nice blanket to help the economics of the deposit. Okay, the final thing will be placer deposits. So these are just the result of alluvial processes that might concentrate high density and chemically inert or hard minerals. And nature is doing the work and depositing them in special locations where it's actually not too hard to extract. So commonly gold, very common case that people see, diamonds, zircon, sapphires, cassiterite, chromite. There's a huge list, ilmenite, monzonite, and a lot of these can be used for industrial applications. So the minerals concentrate in traps associated to superficial environments. So we might have our primary ore body, and then we might have deposits occurring in the bows of rivers or along beach areas, etc. So here's just an example that we have mineral-bearing veins that might have cassiterite or gold in them, and they're weathering out, and we can get concentrations because these cassiterite is heavy. It drops out earlier than many other minerals like quartz, and so it will form in traps where there's a change in the energy of the sedimentary environment. So beach is another classic example. When we concentrate them out, you might get magnetite sands or garnet sands or rutile sands, and that's where it's quite an easy deposit for us to actually mine. So in fluvial places, we are looking for areas where we have change in the energy. So a classic example is the Oxbow Bow, where we have high energy flow on the outside and low energy flow in the inside, and we can drop out the heavy minerals. We could also do it where there's a fork changing from fast to slow, so there's a relative speed change. We might have barriers that inhibit flow, or potholes where we have an eddy formation, etc. We have these subtle changes in the nature of the flow of the water that can lead to heavy materials settling out. It also can be driven by wind, so don't forget those ones. So they're concentrated in these processes. Some of the largest gold deposits, like in Witwatersrand sand in South Africa, are ancient placer deposits. It's quite easy to mine. Mining costs are low. Many of the tin mines in the New England area were actually alluvial tin. Hard rock tin is very difficult to mine. And some can be buried by later deposits, and we call these deep leads. So it's just a fancy name to say that there may be a lava flow on top of them, and we're digging into the old alluvial channels. Here's just some examples of some alluvial gold from Witwatersrand. We also have pyrite and things like that. They're very important. Limited metallurgical problems, typically high grade. They can be high purity minerals. We don't have to crush them or chemically treat the ore. It can largely be done on site, so they're highly favourable, and nature has done the hard part. We don't have to blow stuff up, as fun as that is. We can just go and dig it up, essentially. Some of the common mineral sands that we have: rutile, ilmenite, zircon, garnet for industrial abrasives. People are also looking at monazite for things like thorium, but it's also got some rare earths in it, maybe xenotime, yttrium phosphates. There's a variety of applications, including using titanium for feedstock and etc. So don't discount them. They're very important deposit styles and sources. Here's just some examples. Zircon is used as a pacifier for glazers. There's renewed interest in monazite for use in generating electricity. Like I said, abrasive sands. There's a variety of different uses. Here's just some mineral sands. They're high gravity, electrical conductivity, and I think that's about it. So this is just some different environments that we find them. We've sort of broadly gone through where these places occur. So thank you.